Okay, let's have a look at this HSC Extension 1 question from 1997. And it's question 7, so it's meant to be one of the hardest questions. It's the last question on the paper. Now, they start us off, it's projectile motion, and it's an unusual one because the projectile is not being projected from the ground, it's being projected from a height, and it's being projected without any angles. It's being projected horizontally, the velocity that is just purely horizontal. Now, the first thing oops, what the hell's happened there? Okay, right. The first thing they try and get us to do is to derive these two parts of the projectile motion. So let's start with them. And remember, x is the horizontal and y is the vertical. So I always like to do it in two parts, so just over here. So if we know that acceleration equals 0, and this is just in the horizontal, well, velocity equals the integral of 0 with respect to time. Now, the integral of 0 is going to be 0 plus a constant. Now, we know when t equals 0 that velocity equals v. So velocity equals v. So we put that in and we get v equals 0 plus c. I don't really need that 0, but I get a constant v. And that's right, because my velocity is going to be that v that it's being projected from. Now, to find displacement, I've got to integrate velocity with respect to t. And I'll get vt plus another constant, which I'm going to call c1. And at time 0, when t equals 0, well, there is no displacement, so x equals 0. So 0 equals velocity times 0 plus this other constant, which means my second constant will be 0. So my displacement is just velocity times time. And that's the velocity that this particle is being projected at horizontally. Okay, let's go vertically. Now, we know that vertically, gravity, which is forcing this particle down, is going to be negative g. And we know that's negative 9.8, but we're going to keep it as g. So if we want velocity, we've just got to integrate gravity with respect to t. And again, we get minus gt plus some constant. Now, when t equals 0, when time equals 0, the velocity is equal to 0 because there's nothing acting on it. So we get, and I'm going to call, because I've already used c twice, I'm going to call that c2. I'm going to get 0, and I'm going to get 0 equals 0 plus c2. So my third constant, c2, is always equal to 0. So my equation for velocity in the vertical is just gravity times time. And that's right. Think about it. What's acting on this object, this particle, vertically, and it's just gravity. And what will happen? The velocity will be gravity times time, and the negative gravity just means it's going down. Okay, what about displacement? Well, displacement equals the integral of velocity with respect to time. And that'll give us, all right, we have 1 to the power minus gt squared on 2 plus another constant, so we'll call that C3. And we know when t equals 0, and this is where you've got to be smart, that displacement equals 120. Because if we go back here, oh no, it equals, I'm a step ahead. It's just the height, whatever the height happens to be. I'm jumping ahead. I've already read the second part of the question. So h equals minus g times 0 squared over 2 plus this C3, which means h is going to equal that C3. So it means that y, the vertical displacement, is minus g t squared over 2 plus h, but they want us to write it in a certain way, so h minus a half g t squared. I'm pretty sure that's what they wanted. There we go. So there are our two first values. Now the reason they wanted us to do that is because the second part of the question takes us further along this. So, and it's, you know that this part relates because it's part of the same question. So you're just going to use the same diagram as above there. So I'm just going to use this. So let's have a look. A canister, I'm going to zoom in a bit. A canister containing a light raft is dropped from a plane to a stranded sailor. The plane is traveling at a constant velocity of 216 kilometers per hour at a height of 120 meters above sea level along a path that passes over the sailor. So let's put the sailor here. And it doesn't say whether the sailor's in the yacht or whatever, but there's the sailor in the ocean. And here comes the aeroplane. And the aeroplane is coming along and it's going to pass over the sailor. And the height is 120. And this V is 216 kilometers per hour. Now, straight away, I know I'm in a bit of trouble here. I'm going to have to be careful with my units because gravity is in meters per second and we use velocity in meters per second. So we're going to have to do a little bit of mucking around there with that. Also, when we get to this bit, we've got drift in kilometers per hour, but we'll come to that in a moment. Now, we've got these two equations. They've given us these two, but now my V is 216 kilometers per hour and my height is 120 and my gravity, they want us to use not 9.8 but 10 meters per second. Well, the first part of this question is pretty easy. How long will it take the canister to hit the water? Well, we're only going to use the y value and we've got all the things we need for it. So let's go over here and do part 2. How long will it take for it to hit the water? Well, we want y, which is 120 minus negative 10. It's not minus negative 10 because the minus comes from gravity being negative. Or being down. Come on, thank you. Minus a half times 10 times t squared. Now we want it when it hits the water. So when y equals 0. So we go 0 equals 120 minus 5t squared, because a half times 10 is 5. Take the 5t over the other side. 5t squared equals 120. T squared is 120 divided by 5. I'm not going to take the risk of getting that wrong, so I'm going to use my calculator. 24. And t equals the square root of 24. Now we know we get two answers, plus or minus. But we know that t time can only be positive, so it's just going to be root 24. And we can get that just by square rooting our answer. 4.898979. So we go 4.9 seconds. I'd probably leave it as root 29. So 4.9 seconds. That's how long it's going to take for this particle to hit the ground. So that's our vertical displacement. So what else have we got here? A current is causing the sailor to drift at a speed of 3.6 kilometers in the same direction the plane is traveling. So this sailor is drifting this way at 3.6 kilometers an hour. The canister is dropped from the plane when the horizontal distance from the plane to the sailor is d. Okay, so this distance, the plane to the sailor, is d. All right, so we've got a couple of things happening here. What values can d take if the canister lands at most 50 meters from the stranded sailor? Okay, so what we're going to have to do, we're going to have to use this down here, this one. But we're going to have to do some conversions first. So now the velocity of the plane is 216 kilometers an hour. Now we have to convert that to meters per second. So it's 216. Let's convert it to meters, so times by 1,000. And I'm going to divide by 60 to get it into minutes, and divide by 60 to get it into seconds. So 216 times 1,000 divided by 60 divided by 60 again. And that's 60 meters per second. Now, when I get that, I think to myself, I'm pretty happy, because I'm pretty sure they planned that with that 216. I'm pretty sure they planned that it'd come out as a nice, neat number. So I'm feeling pretty confident if you do that in the exam. Now, we know that it's going to take 4.9 seconds for this thing to hit the ground. And we know that x equals vt, which is 60t. So the horizontal distance, remember that's what x is, it's a horizontal displacement. When t equals root 24, and that's how I'm going to put in my calculator, x equals root 24. 60 times root 24. I know it makes no difference, but I want to keep it nice and neat. 60 times root 24. So 60 times square root 24. And I get 1,440. That's not right. Let's try that again. 60 times root 24. There we go. That's better. 293.9. 293.9. What else was in there? Let's show them how smart we are. 387691. Righto. So that's how far this thing is going to travel when it gets dropped. So it's going to go, it's going to land there, and it's going to land at 294 meters from when it leaves the plane. Now the sailor is a d distance away, but the sailor's also moving. So how far has this sailor moved? Well, let's have a go. The sailor is drifting in the same direction at 3.6 kilometers per hour. So 3.6 kilometers per hour. Well, that velocity equals, well, we have to change again. So 3.6 times 1,000, let's get it in meters, over 60 times 60 equals, so 3.6 times 1,000 divided by 60 divided by 60. 1. And again, when I get that, I'm pretty happy because again, and you can tell because it's got 3.6, 1 meter per second. Now, how far do you travel? Well, the sailor's distance, the sailor's x, is 1 times root 24. That's how far the sailor's going to drift. So, and we already know what root 24 is. It's 4.9. So the sailor will go, and we'll just do it. So 1, you know what root 24 is. We did it before. 4.89. So let's go 4.9 meters. So here we go. And I'm just going to draw the horizontal. I'm going to put all the things in. So here's this distance here. Here is the sailor in the water. But the sailor has moved on 4.9 meters. And the canister with the life raft needs to land within 50 meters of the sailor. So the sailor is going to be here. So the sailor has to be 50 meters from where this thing's going to land. Now, the canister is going to land 294 meters. So let's assume it could be smaller, it could be bigger. It's going to land here. Let's say that's 294. So the sailor has to be within, or this could be 294. It doesn't matter. So the distance is going to be d plus 4.9. And that has to be between 294 minus 50 and 294 plus 50, because it's got to be within 50 meters either side. So if the canister drops here, or the canister drops here, and it's got to be within 50 meters of where the sailor is, that has to be 50. And this whole distance here, d plus 4.9, okay, that's where the sailor is. If it drops too early, if they drop it and they get the distance wrong, we're trying to find out at what distances between. If they drop it, what's the minimum, the minimum distance, or the maximum, that's going to be the maximum distance, or the minimum distance between them and the sailor. So let's see what happens. So here, 294 plus 50, 294 plus 50, 344 meters, the distance. Oh, sorry, I was meant to do minus, that's 344, that's that one. And this one is, just go back and change it to minus 244. I know I could have done that in my head, but I want to just make sure I'm right. Now, I'm minus 4.9 from both sides. Minus 4.9. 239.1. And D will be 344 minus 4.9, 339.1. Now, if you think about it, here's a plane, here's a sailor, and they've got to get this distance right to land it. Now, the sailor's drifting, so the sailor, in the time it drops, will travel 4.9 metres. So we want it to land within 50 metres of this sailor, where the sailor will be in the water. So we have to get this distance right. Now, if we drop it a long way away, what's the maximum distance that this can be? Well, it can be 339. So, or if we wait, what's the closest we can get to the sailor? Because remember, it's going to travel past the sailor. So we have to be between 339 metres from the sailor and 230. We've got about 100 metres. Well, not about, exactly 100 metres to play with to get it right, when to drop it, so that it lands either within 50 metres there or 50 metres there. Remember, we're trying to be within 50 metres of this position. And that's it. Now, if we have a look at, and I've got them up, the answers for that. I had that image up. Where was it? The solutions to that. Where do we go? I've already got it opened up. How do I get out of this?